All right, guys, we've got a big set of notes here. Number 9, the weak acid-base titration. So we've talked about weak acids and bases. We talked about their original definitions. Where did we talk about that? Here. With the fact that they're weak, meaning not all of the acid molecules or base molecules dissociate into their ions. We talked about finding their pH in previous notes, where we have to use an icebox to figure out what the concentration of the H plus or the OH minus, if it's a base, is at equilibrium, and then that's what we use to find the pH, the H plus concentration at equilibrium, or the OH minus concentration, which then is of course related to POH or pH. We've already talked about titration curves, where we're reacting an acid with a base, and now we're going to look at titration curves for weak acids or weak bases. This picture shows the appropriate response to the thought of having a weak acid titration with a weak base. There would be 2 equilibria that we have to worry about. So we don't do that. We will either use a weak acid or a weak base, and strong of the other one in order to have a simpler scenario. 2 examples here. You can see a weak acid reacting with a strong base. It's the same sort of neutralization reaction. We make sodium acetate, the salt, and remember that a salt just means it's an ionic compound. A soluble ionic compound here doesn't have to be NaCl, table salt. So it makes a salt and it makes water. And the tricky thing is that it is the salt that will impact the pH of the resulting solution, and the resulting solution is our salt water, right? These guys here we're making. So even if you titrated perfectly the weak acid and the strong base, and you had no weak acid and no weak base left over, the salt itself, because it has the conjugate of the weak acid or the weak base, whichever one it is in this case, is the conjugate base of the weak acid, acetic acid. Because of the presence of that guy, it's going to split water. Remember HOH, right? So you're going to be, so they're going to take up H plus from the solution and leave the OH minus behind, which would create a basic solution, or it's going to take up the OH minus and leave the H plus behind, which would create an acidic solution. So it is the salt that will determine the pH of the products. Now, when you have a strong acid reacting with a strong base, the conjugates that would be present there are so weak they can't split water. But because we have, in this case, in this example up here, a weak acid, his conjugate base, the acetate ion, is strong enough to split the water. He will take up the H pluses and leave some OH minuses behind, and so that would create a basic solution. The reaction down here is slightly different. It's not the same format that we're used to seeing, but it is a reaction between a strong acid and a weak base. So what would happen here is the weak base would take up the H plus from the hydrochloric acid and become the ammonium ion. He has a positive charge, and then because there would be these chloride ions left over, the conjugate of the acid, once he gave up his H plus, these 2 guys would be attracted to each other, and that's where we would get this ammonium chloride salt. So that follows a little bit of a different pattern than what we're used to seeing, but it's the same business going on: strong acid reacting with a weak base. So we've already mentioned this a little bit, but the salt would have a pH when the anion is the conjugate of a weak acid, so like the acetate ion, We call this salt hydrolysis when a conjugate is strong enough to break water. So if you think about the word hydrolysis, hydro means water, and lysis is to split apart. You might have heard in biology of an organelle called the lysosome. The lysosome is a place that can degrade. It's a little organelle that's got a very low pH, and it can degrade chemicals that the cell deems unfit to stay in the cell. So when you have the conjugate base of a strong acid, it will not split water because it's too weak. It's super, super weak. It cannot split water. But when you have the conjugate base of a weak acid, then it will take the H plus off of the water and recreate the acid molecule, which, remember, it can stick around because it's weak, right? It's a weak acid. And then it releases this to the solution. And because it releases the OH minus to the solution, it creates a basic pH. Creates a basic pH. When you have we'll just focus here on the weak acid and strong base. Do I have? Oh, I do. I bring up. Okay, good. Well, because we'll look at that too. Sorry. Okay, moving ahead. Coming back. Sorry. So let's look closely at what's happening at the equivalence point. Remember, at the equivalence point, the moles of the acid are equal to the moles of the base. So that means that they are in their perfect stoichiometric ratio. And so the only thing that we have to consider are the products. And so then we're going to look at the salt. The salt that's created at the equivalence point is just the salt in the water, right? We've perfectly neutralized the acid and the base. And so we look at the salt and we notice, what does he split into? He splits into sodium, the conjugate acid of the strong base, sodium hydroxide. So sodium won't impact the pH, but the acetate ion is the conjugate base of a weak acid, so it will undergo hydrolysis. It will split water. And what is it going to do? It's going to produce the OHs, like we just said. So what that means is that at the equivalence point for the reaction between a weak acid and a strong base, you will have a basic pH. And it's so confusing to students because they want to look at that and say, oh, well, it's a basic pH at the equivalence point because we added a strong base. But that's not the reason why. It's not that the strong base is like overpowering the weak acid. Remember, at the equivalence point, we have equal moles. So it's not the base and the acid from the reactants that are playing any part in the pH of the equivalence point. The thing that's impacting the pH of the equivalence point is the salt, specifically the conjugate base of that weak acid. And because it is a conjugate base, it's making a basic solution. So when we look at a titration curve of a weak acid with a strong base, notice how high the equivalence point pH is. It is above 7. So let's look through these questions over here. The first question says that the titrant, so the thing that we have in our burette up here, is a strong base. And then the thing that we have in the analyte is a weak acid. First of all, we know that the titrant is a base and the analyte is an acid because the pH starts low. All right, we have a low pH to begin with. That means we have an acid in the analyte. Now, the way that you know the strong base and the weak acid, and that it's not a weak base with a strong acid, or it's not a strong base with a strong acid, The reason that we know it's a weak acid is because the pH at the equivalence point is greater than 7. It's basic. And then the answer to the last question down here, it's not because of the strong base that we have a basic equivalence point, although you can remember it that way if you want to, but that's not the reason why. The reason why is because of the weak acid. The weak acid gives a conjugate base. My surface just froze. Oh no. Hold tight. Okay, let's try this again. It's because the conjugate acid, the weak acid gives a conjugate base that will split water. That is why the equivalence point is above 7. It's basic. Now, all of this is just in reverse for the strong acid and weak base. So scroll down and look at that. An example that we looked at earlier. It's a little bit of a different format for the neutralization reaction that y'all are used to seeing, but the same principles apply. When you have an equal or an equivalent moles of your strong acid and your weak base, the only thing we have to worry about is the salt that's present, and we need to consider how does the salt interact with water. And in order to do that, we consider the two ions that are created. We have the ammonium ion and the chloride ion. Now, the chloride ion is the conjugate base of the strong acid HCl. So that guy is not having any impact on the pH. But NH4 plus is the conjugate acid of the weak base ammonium, and I think I said that wrong, sorry, is the conjugate acid of the weak base ammonia, and ammonium, the ion, is strong enough to split water, and he's got a positive charge, so when he separates water into HOH, which one is he going to like? Well, he's going to pick up the negatively charged one and make ammonium hydroxide and release the H plus to the solution. When that's released to the solution, it will make the solution acidic. And it makes sense, right? Because it's a conjugate acid. And so we've released a conjugate acid that is strong enough to impact the pH. Sorry if y'all can hear all the background noise. It is strong enough to affect the pH, and it's going to make it acidic because it's an acid. So let's look and see what that would look like on a titration curve. Same kind of business that we looked at before. Notice pH at the equivalence point is below 7. Notice that the pH starts low and gets higher as you add the titrant. So that means that we're starting with an analyte that is an acid, and we're adding a titrant that is a base. This time, we know that it's a strong acid and a weak base because the pH at the equivalence point is less than 7. And the reason that it's acidic is because of the base, because of the conjugate acid that it forms, interacting with water, stealing away the OH minus and releasing the H plus to solution. So now we have three, I'll just add this right here. Now we have three different types of titration curves. Oh, can I not split that? All right, so titration curves. At the equivalence point, if the pH is equal to 7, then that means you are adding a strong acid and a strong base. Now, which one is the titrant and which one's the analyte? You have to figure out. Does it start low and get big, or does it start high and get small? Right? If it starts low, that means the acid is the analyte. Now, if you have a pH that's greater than 7, then that means, I need to get my pen back, then that means that you have a weak acid and a strong base. But if you have a pH at the equivalence point that is actually acidic, it means that you have a strong acid reacting with a weak base. And again, the reason that the pHs differ at the equivalence point from 7 is not because of the strong guy, it's because of the weak guy. It's because of the conjugate of the weak. Summary here, we've talked about if you are reacting a strong acid, then its conjugate base is so extremely weak that it's not going to change the pH from 7, right? Water. If you have a strong base, same difference, extremely weak, looking at a pH of 7. But if you have a weak acid or a weak base, then the conjugates are strong enough to split water, and it's going to cause a weak acid's conjugate base is going to cause the pH of the equivalence point to be above 7. And the weak base making the conjugate acid that's strong enough to split water means that the pH there would be below 7. It feels kind of backwards, but the more you look at it, the more you think about it, the more it's going to kind of click into place. At least you can find a way to memorize it and push the I believe button.